Log on, tune in, find out. Another good idea from Cambridge.
This is Peter Goos from the University of Antwerp, and he will be talking about optimal design of block and split plot experiments for fixed effects and variance components estimation. Over to Peter.
Thank you. That's indeed the title of my talk, but I would immediately like to start by giving a little bit more, a more specific title. I've added here on the next slide the term response surface experiments to make clear to those of you who are more familiar with categorical treatment factors in split plot context. So I will only talk about response surface experiments, quantitative experimental factors, and also all the examples I will give will be for full quadratic models. So hence the term response surface. Here is an outline of the talk. I will start by introducing blocked and split plot experiments. Then I will show you the model that we use to analyze data from blocked and split plot experiments. And then I will introduce the various optimal experimental design approaches that you can use for blocked and split plot experiments. I will discuss fixed effects estimation and variance components estimation. And to find all these designs, we need to do a lot of calculations, and we can reduce the amount of calculations by using a few clever techniques called Gauss-Stieltjes-Wigert quadrature and Gauss-Jacobi quadrature. I will also explain what these are, and then finally I will show you some computational results. First of all, blocked experiments. I think most of you know that we need blocked experiments whenever all the experimental runs cannot be conducted under the same circumstances, under homogeneous circumstances. If that's the case, we try to group the runs so that the runs within a group are more alike than runs from different groups, and we typically call these groups blocks. And the blocks can be days, the blocks can be batches, the blocks can be test subjects, they can be basically any type of factor that groups the runs into homogeneous groups. And in this talk, I will restrict myself to just one blocking factor, one way of grouping the runs. Split plot experiments are useful in various circumstances, and in the literature on industrial response surface experiments, split plot experiments are very often associated with hard-to-change factors. Hard-to-change factors are factors whose levels are hard to change. For example, the factor temperature is a temperature that's typically whose level is hard to change because it takes a while usually to heat up an oven or to let an oven cool down. That's a hard-to-change factor. And people in industry do not like to change the levels of such factors all the time. They do not like to reset the levels of these factors for every run that they do. What they like is they like to set the oven to a certain temperature, the hard-to-change factor to a certain level, and keep it constant for a number of successive experimental runs. And that also leads to a split plot type of experiment. If you do this, then the groups of the runs of your experiment are also grouped, and within each group the level of the hard-to-change factors remains constant. So that's why hard-to-change factors give rise to split plot experiments. But split plot experiments are also useful in other contexts where you do not really have such hard-to-change factors. Split plot experiments can also be useful, for example, when you experiment with two-stage production processes where some of the experimental factors are applied in the first stage and some other experimental factors are applied in a subsequent stage. So these are split plot experiments. What models do we use to analyze data from such experiments? Well, I think most of you know the kind of models we use. We have a certain response y, and I have given the y here two indices, ij. The I corresponds to the block in which the response is measured, and the j corresponds to the number of the run within the block. So here we have yij, that's the jth response in the ith block, and we model it like this: a sum of three components, f of xij times beta. The is the first component. In this first component, xij gives the levels of the experimental factors at the jth run in the ith block. And as I said in the beginning of the talk, f of x is a polynomial expansion, and the polynomial expansion I will use in this presentation is the expansion we need for a full quadratic model. So f of x basically leads to terms like an intercept, main effects, two-factor interactions, and quadratic effects. All these, the effects are contained within the beta vector. These are the effects that we want to estimate ultimately. These are the fixed effects in the model. And on top of these fixed effects, we also have some random effects. Here we have gamma I, that's the block effect, the effect of the ith block. And we have a random error, epsilon ij, the random error for the jth observation, the jth response in the ith block. And we assume that each of these random effects, the gammas and the epsilons, are normally distributed with zero means. For the gammas, we have variance sigma squared gamma. For the epsilons, we have variance sigma squared epsilon. That's the model we typically use for these experiments. That's the model that's valid for both blocked experiments and split plot experiments. But when we talk about data from split plot experiments, we typically like to be a little bit more specific. We like to use a slightly different notation for the experimental factors. Instead of just using an x vector for the experimental factors, we like to use two different kinds of vectors to emphasize that in split plot experiments we have two types of factors. One type of factor applied to the blocks, which we call whole plots in split plot experiments, and these are the W's. So W has just one index, I, because the levels of the W's, the hard to change factors, are specific to the blocks or whole plots. And then on top of that, we have the subplot factors, the experimental factors that we apply to the individual runs, and these have two indices to emphasize that their levels are set independently for every run. So these are the whole plot factors, the W's, and the S's are the subplot factors. And we still have gammas and epsilons, which now get different names when we talk about split plot experiments. We typically call the gammas whole plot effects, and the epsilons we still call these random errors. The assumptions behind the gammas and the epsilons don't change, so we still have the same random distribution for the whole plot effects and the random errors, and we still have variance components sigma squared gamma and sigma squared epsilon. On top of these assumptions, we also assume that the gammas and the epsilons are independent from each other. That's a classical assumption in this context. We can also write a model like this. Y is equal to x times beta plus z times gamma plus epsilon. Y is, of course, the vector of all the responses. X is the model matrix. Beta is the vector of all the factor effects. Z is a matrix of zeros and ones, which assigns the runs to the blocks in a blocked experiment and to the whole plots in a split plot experiment. And then we have two vectors, gamma and epsilon, that contain the random effects in the model. Under all the assumptions that we've made for the model, the variance-covariance matrix of the response vector has this form: sigma squared epsilon times the identity matrix plus sigma squared gamma times z transpose. That's the variance-covariance matrix, but we can rewrite that information, that variance-covariance matrix, a little bit. That's useful for later on in the presentation. We can bring sigma squared epsilon out, and then one way of rewriting the variance-covariance matrix is this way. When we bring out sigma squared epsilon, between brackets we get the identity matrix plus eta times z transpose, where eta is the ratio of the two variance components, sigma squared gamma and sigma squared epsilon. Why do I explicitly do that here? Well, because optimal designs don't depend on the absolute magnitude of the variance components, so they don't depend on the absolute magnitude of sigma squared epsilon, but they only depend on the relative magnitude of the variance components. And one way of expressing how big the variance components are relative to each other is by using this variance ratio eta. We can do this also in another way. We can make use of the so-called intra-class correlation coefficient, which I denoted by rho here. And in that case, the variance-covariance matrix looks like this. And rho is sigma squared gamma divided by sigma squared gamma plus sigma squared epsilon. That's an alternative way of writing this variance-covariance matrix. So that's the model. We have correlated responses under this model. This variance-covariance matrix tells us that runs within the same block or within the same whole plot give correlated responses, and runs from different blocks or from different whole plots are independent. And because of the correlation, we need generalized least squares. That's the generalized least squares estimator, which has this variance-covariance matrix. And in these expressions, I've used v hat 3 times. And v hat is, of course, the estimated version of the V matrix, the estimated variance-covariance matrix. To estimate that V matrix, we need to have estimates for sigma squared gamma and sigma squared epsilon. And we can get these estimates in general by using a restricted maximum likelihood. That's a method that always works in response surface contexts, even if your split plot experiment is not perfectly orthogonal, if your blocked experiment is not perfectly orthogonal. So that's it for the estimation. How can we now design blocked experiments and split plot experiments? Well, in the literature, various approaches have been used. For split plot experiments, for example, there has been a publication by Trinke and Gilmore about stratum by stratum construction of split plot designs and more general multi-stratum designs. There have also been a couple of publications on equivalent estimation designs. I think that the bulk of the work started with the publication by Vining, Kowalski, and Montgomery in the Journal of Quality Technology in 2005, and there were several follow-up papers by Parker, Kowalski, and Vining on the same subject. These papers dealt with how you can arrange central composite designs and Box-Binkin designs in a split plot structure so that the generalized least squares estimator is equivalent to the ordinary least squares estimator, and that's where the name equivalent estimation designs comes from. Besides these two approaches, the stratum by stratum construction and the equivalent estimation designs, there has also been work on the from the optimal experimental design angle, and that work has been done, for example, by me in my PhD work a couple of years ago, 10 years ago by now. For blocked experiments, the emphasis has for a very long time been on orthogonal blocking. For example, in all textbooks about experimental design, response surface design, I should say perhaps, the emphasis has been on orthogonal blocking for central composite designs and for Box-Binkin designs, but also for blocked experiments I did some work a long time ago using the optimal experimental design approach. And here are the exact references of the work I did at the time for blocked experiments and for split plot experiments. The approach I took was I tried to find the optimal blocked experiments and the optimal split plot experiments, and that meant that I was seeking designs that maximize the determinant of the information matrix on the betas, on the factor effects. And the information matrix on the betas looks like this: x prime v inverse times x. Now, if you use that approach, there are at least two weaknesses. First weakness I can best illustrate, I think, by giving you a small example. And the small example is a blocked experiment involving 8 runs, partitioned in 4 blocks of size 2, for estimating a full quadratic model in 2 quantitative factors. That model, the full quadratic model involving 2 factors, has 8 parameters in total, we need to estimate one intercept, we need to estimate two main effects of the two factors, two quadratic effects, a two-factor interaction effect, and on top of that we need to estimate sigma squared gamma and sigma squared epsilon. So 8 things in total that we have to estimate, and we have just enough runs to do that. Well, that's the design that you find if you use the optimal design approach that I described on the previous slide. That's the design involving 4 blocks of size 2 and 2 quantitative factors. If you look at this design, that design does not look too bad. Nothing seems wrong with the design, and yet there is a major problem with the design. With that design, you cannot estimate the variance components, even though you have enough runs to do it. You can't estimate the variance components, so you can't do proper statistical inference. So that's the first major weakness of the old approach to designing split plot and a blocked experiment. There's a second weakness, which is, in my opinion, less serious, but it's still a weakness. The optimal blocked experiments and the optimal split plot experiments, they do depend on the variance components. They do depend on the relative magnitude of the variance components. And that's very unelegant, because if you want to set up a split plot experiment or a blocked experiment, you typically don't know the relative magnitude of the variance components. Fortunately, it turns out that in some cases, the optimal designs do not at all depend on eta. In other cases, the optimal designs do depend on eta, but a design that's optimal for one value of eta is very highly efficient for another value of eta. So the fact that you miss the optimal design is not too bad. You will end up with a design that's good anyway. So this is, of course, unelegant, the dependence on eta or on the intra-class correlation coefficient rho, but the practical consequences are not too severe, I'd say. And in the literature, it's typically recommended to set eta equal to 1 or rho equal to 1/2 when you want to find the optimal designs for split plot experiments and blocked experiments. That usually works very well. But the dependence on eta remains a weakness, and it's a weakness that referees of papers tend to notice all the time. How can we solve the problem? How can we remediate the weaknesses? Well, what we can do is we can take into account the estimation of the variance components when setting up the experiment. That's solution number 1. And to solve the problem of the dependence on eta, well, we can, instead of using a point prior guess for the eta value, we can use a Bayesian approach, or I should say a pseudo-Bayesian approach, or a semi-Bayesian approach, or a robust design approach, involving a prior distribution for eta or for the intra-class correlation coefficient rho, to try to reduce the dependence of the design on the exact eta value that we use. Let us have a look at these solutions. First of all, how do we take into account the variance component estimation when we set up the design? Well, for that we need an information matrix for the variance components, but to construct an information matrix for the variance components, we need to have an estimation technique in mind. And, well, as I said, we use restricted maximum likelihood, usually in response surface contexts, to estimate the variance components. And that's where we based the information matrix on. That's the information matrix we use is specific for restricted maximum likelihood. Expressions for the information matrix can be found in various places. For example, in the book by Searle, Casella, and McCullough. There you can find general information matrices for restricted maximum likelihood. And if you then turn this general information matrix that you can find in the book into the specific information matrix for split plot experiments and for blocked experiments, this is what you get. A 2x2 information matrix, because we have 2 variance components, of course. And the p in this expression has this form. So the p does depend on the variance covariance matrix V, which depends on the variance components. So which depends on eta and on the intraclass, or on the intraclass correlation coefficient, rho. So also this information matrix depends on the relative magnitude of the variance component. Now what did we do now that we have this information matrix for the variance components? Well, we created a composite design criterion that takes into account the information matrix for the fixed effects, the factor effects, and the information matrix for the variance components. And that's the composite criterion we used. We raised the determinant of the information matrix for the fixed effects to the power of 1 over p, 1 over the number of fixed parameters, that is, and we multiply it by the determinant of the information matrix for the variance components raised to the power 1 over 2, because we have 2 variance components. So that's our composite criterion. And if we want to emphasize that this composite criterion depends on eta or rho, we can of course use this notation, d of eta or d of rho. So that's the composite criterion. That's solution number 1 to avoid trouble with estimating the variance components. For the dependence on eta or rho, we use this pseudo-Bayesian approach or semi-Bayesian approach involving a prior distribution for either eta or rho, and I denote the prior distributions like this: pi of eta or pi of rho. And the way we use these prior distributions can be seen here. Our first Bayesian composite criterion looks like this. We try to maximize the average log determinant, the average log composite criterion value evaluated over the prior distribution for pi. And this prior distribution for pi goes from 0 to plus infinity, because the variance component eta can take any positive value. If we use a prior distribution for rho, the expression looks a little bit different, because rho is the intra-class correlation coefficient. It always lies between 0 and 1, so the limits of our integral are different here. But otherwise, the second criterion here is the same. We try to maximize the average log of the composite criterion d of rho evaluated over the prior distribution. So that's the Bayesian composite criterion that we use. The problem with this Bayesian approach is that there are no analytical expressions for these integrals, and because of that we have to evaluate these integrals numerically, and very often this is done using pseudo-Monte Carlo sampling, and pseudo-Monte Carlo sampling is very computationally intensive. How does that approach work? Well, what we do in pseudo-Monte Carlo sampling is we take a lot of draws from the prior distribution. For example, when we have a prior distribution for eta, we take a lot of draws, eta I, from that prior distribution pi of eta. And then we evaluate our design criterion at each of the draws, at each of these eta I values. And then we average our design criterion over all these function evaluations, over all these evaluations of the composite criterion. And this is very time consuming, because for every eta value we have to evaluate 2 different determinants, and one of them can be pretty high dimensional. The information matrix for the fixed effects can be pretty high dimensional, so we lose a lot of time if we have to do this over and over again for a lot of different eta values. And in the pseudo-Monte Carlo approach, it's really important that you use a lot of eta values, because otherwise you can't evaluate that integral very precisely. So if you want to have a good evaluation of your design criterion, you really need a lot of eta values. So usually the R in this expression is big, like 1000 for example. So that's very time consuming. We didn't want to do that. Instead, we used quadrature techniques. And quadrature techniques are techniques that save you a lot of time. Instead of using 1000 draws from the prior distribution, we just use a couple of draws from that prior distribution. And the difference is that couple of draws that we use in quadrature approaches, that couple of draws is chosen systematically, is chosen in a clever way rather than random. But the way in which you have to choose the draws differs from prior distribution to prior distribution. What you can see here on the slide is what you have to do if you have a log normal prior distribution on eta. If you have a log normal prior distribution on eta, then our composite criterion looks like this. So we still have the integral from 0 to infinity of the logarithm of our composite criterion, evaluated now over the log normal prior distribution. For this prior distribution, there are two techniques that you can use. One technique involves Gauss-Hermite quadrature. That's a technique with which you can reduce the number of draws from, say, 1000 to about 8. However, it's slightly better to use another approach than Gauss-Hermite quadrature, and that other approach is called Gauss-Stieltjes-Wigert quadrature. And what does that technique involve? Well, in that technique, we need systematic draws from the prior distribution as well as weights for each of these draws. And in this formula down here, that's how we evaluate our integral of the composite criterion. In this formula, you can see a certain value alpha. This is what we call the abscissa. And here you can see a W, and this is the weight for a particular abscissa. And how should we use the abscissas? Well, we need to take these abscissas, which I denoted by alphas, and multiply them by e to the power mu, and the mu is the first parameter of our log normal prior distribution. And then we need to evaluate our composite criterion in this specific value, e to the power mu times the abscissa. And then that function evaluation gets this very specific weight W. Now, where do these weights come from? Where do these abscissas come from? Well, they come from a specific kind of orthogonal polynomial, and that specific kind of orthogonal polynomial is the Stieltjes-Wigert polynomial. That's where we get these abscissas and weights. And it turns out that you can get away with just 4 different abscissas and hence also 4 different weights to evaluate our integral, our Bayesian composite design criterion precisely. So we can reduce the computational burden with a factor 250 compared to pseudo-Monte Carlo sampling. So that's for log normal prior distributions. A problem with prior distributions, of course, is that we need to come up with specific values for the parameters of the prior distributions. Here we have 2 parameters in our prior distribution, a mu value, which I have already pointed out, and on top of that we also have a sigma value in our log normal prior distribution. It's always a little bit difficult to choose these values, but for the log normal distribution it's a little bit easier, I think, than usual. Because it turns out that there are alternative parameterizations of the log normal distribution, and these alternative parameterizations make use of the geometric mean and the geometric standard deviation, which here I've denoted by m and s. The geometric mean is e to the power mu, and the geometric standard deviation is e to the power sigma. And there's a result that says that 99.7% of all the probability mass for a log normal distribution lies between m over s cube and m times s cube. Now you can use this to come up with sensible values for mu and sigma. For example, if you expect your variance ratio eta to be around 1, then you should choose the geometric mean to be 1. The geometric mean is a measure of location, so it makes sense to set it to 1. And if you set the geometric mean m to 1, then using this equation here, you can see that you should set mu to 0. And then we have a sensible choice for our first parameter, mu. Then if we expect that our variance ratio will lie between 0.1 and 10, for example, then we should choose s as follows. S should be the cube root of 10, or alternatively, sigma should be the logarithm of the cube root of 10. And then you have a decent choice for the parameters of your log normal prior distribution. We can also use prior distributions for the intra-class correlation coefficient instead of prior distributions for eta. A sensible prior distribution for the intra-class correlation rho is the beta distribution. And if you use that beta distribution, then this is the Bayesian composite design criterion. And we can see that this prior distribution, the beta distribution, has parameters kappa and lambda. Well, here we face the same problem. We could use pseudo-Monte Carlo sampling to evaluate this integral, but it's better to use a quadrature technique. And this time we need to use Gauss-Jacobi quadrature, which is very similar to Gauss-Stieltjes-Wigert quadrature, but the weights now come from the Jacobian polynomials. We still have alphas and we still have w's, but they look differently. And here also we can get away with very few draws, with very few alphas, so that we have to evaluate our composite design criterion only very few times to find good experimental designs. So, and here too we can make clever choices of the parameters of our prior distribution. We know that when we have a beta distribution, that the expectation is kappa over kappa plus lambda. We also know that large values for the sum kappa plus lambda correspond to small variances. And then if we expect eta to be around 1 or the intra-class correlation coefficient to be around 1/2, then we should make sure that kappa over kappa plus lambda is also equal to 1/2. And we can do that by setting kappa equal to lambda. And if we have little prior uncertainty, then we must make sure that kappa plus lambda is large. So that's how you can choose kappa and lambda here in this case for beta prior distributions. So that's it for the technicalities. That's it for the approach that we took, the approach that circumvents problems with variance component estimation, and that also deals with the uncertainty we have about the eta values. Let us now take a look at the examples. And the first example is an example I already discussed. 8 runs, 4 blocks of size 2, and a full quadratic model in 2 quantitative factors. That's the example where I had a design that could not estimate the variance components. If you use the new design criterion, the Bayesian composite design criterion, then this is the design you get, independent of the prior distribution you use. So this design is very robust to the prior choices you make for the distributions. And the nice thing about this design now is that it is able to estimate the variance components, unlike this design that I showed you before, the design that we got by just using the information matrix for the fixed parameters. In the next table, and I should emphasize that the reason why this second design can estimate the variance components is that there is a very special block in that design. In that design, we have a block with 2 identical runs, 2 runs at the low levels of the two experimental factors. That is the secret to success here. That's the block that makes sure we can estimate the variance components. In this table here we have a side-by-side comparison of the two designs. Here I compare the new design, which is optimal for any prior distribution that you can think of, and here in this line we have the results for the old design that just focuses on fixed effects estimation. All the values in this table and also in the next such table that I will show you are obtained using eta equal to 1. So here I chose to set eta equal to 1. Now what we can see here is if we look at the composite criterion, for example, for the new design we do get a criterion value which is finite, minus 0.39. For the old design we have minus infinity because that old design is very bad. It doesn't allow me to estimate all the parameters in the model. When we look at the fixed effects estimation, we can see that the value for the old design is better. 5.31 compared to 4.25, and of course that should not come as a surprise because the old design focused all the effort on fixed effects estimation. So this design, the old design, does better when it comes to estimating the fixed effects than the new design. But the strength of the new design is that it allows us to estimate the variance components. So we have a non-singular information matrix for the variance components here, as opposed to the old design, which produced a singular information matrix for the variance component. That's the first example. The second example is an example of a split plot design. Again, 8 runs, this time 4 whole plots of 2 instead of 4 blocks of 2. I have one quantitative whole plot factor, W, and one quantitative subplot factor, S, and again a full quadratic model and 8 parameters to estimate. This time we obtained 3 different designs. On the left we have the design that's optimal for the old criterion that focuses everything on the fixed effects estimation, and in the middle and on the right we have 2 designs that are optimal under the new Bayesian composite criterion. The design in the middle is optimal if we expect small variance ratios or small intra-class correlation coefficients. The design on the right is optimal if we expect large variance components or large intra-class correlation coefficients. This time, in this example, the design we got using the old criterion did allow us to estimate the variance components. So this design with the old criterion did not have a singular information matrix for the variance components, unlike in the previous example involving blocks instead of whole plots. So for the blocked experiment, we had more problems than for the split plot experiment. And on this slide, we have a side-by-side comparison of the 3 designs. We have 2 new designs, one that's optimal for small prior values of the variance component eta, and one design that's optimal for large values of the variance component eta, and then we again have an old design obtained using the old design criterion. When we look at the composite criterion, which has been calculated again for eta equal to 1, and I consider eta equal to 1 to be relatively small, we can see that in that case the first of the new designs does best, has the highest value, and the old design is the worst. So you can see that the fact that we do not take into account the variance component estimation with the old approach is really clearly visible here in this poor performance on the composite criterion. When it comes to estimating the fixed effects, we can again see that the old design does best. So we sacrifice some information on the fixed effects when we want to estimate the variance components well. So that's visible here in the lower values of the design criterion for the fixed effects. And for the variance components, it's of course the other way around. The values here are better for the new designs than for the old design, indicating that the new designs do better in terms of variance component estimation than the old design. And then I have one final example number 3. Example number 3 is again an example for a blocked experiment, 24 runs, 6 blocks of size 4, 5 quantitative factors, and again a full quadratic model. In the model now, in total there are 23 parameters to estimate, and with 24 runs that should be just possible. And the 23 parameters are an intercept, 5 main effects, 5 quadratic effects, 10 two-factor interaction effects, and again 2 variance components, sigma squared gamma and sigma squared epsilon. Now I will not show you the designs now, but I will show you a few computational results. What we did is we calculated 2 designs for this case. One design with the old criterion, focusing completely on the fixed effects, and one design with the new Bayesian criterion, so hence the names new and old here in this table. And for both designs we simulated data, assuming that the total variance of the responses was 10, and using variance ratios of 10, 1, and 0.1. Now, what happens if we generate data with a variance ratio of 10? Well, if we generate data with a variance ratio of 10, then our sigma squared gamma was around 9, and our sigma squared epsilon was around 0.9. So when we estimate the variance components from the simulated data, we should get results for sigma squared gamma in the neighborhood of 9 and for sigma squared epsilon in the neighborhood of 0.9. Now what do we see? With the new designs that take into account variance component estimation, we can see that we do quite well. On average, the estimates for sigma squared gamma are 11.7 and for sigma squared epsilon are 0.9. That's in the neighborhood, with a little bit of goodwill, that's in the neighborhood of 9 and 0.9. For the old design, however, things seem to go completely wrong. On average, we get 4.7 for sigma squared gamma and 19.5 for sigma squared epsilon. So here you can clearly see that the new design criterion helps a lot when it comes to estimating the variance components. And the estimated eta ratio is also completely different for the new and the old design. For the new design, the estimated eta ratio is 10.6, and that's in the neighborhood of the value of 10 that we used to generate the data. For the old design, we get on average 0.22, which is not at all in the neighborhood of 10. For eta equal to 1 and eta equal to 0.1, we get similar results. For example, when we look at eta equal to 1, then both sigma squared epsilon and sigma squared gamma should be in the neighborhood of 5, and we can see that with the new design, our estimates for sigma squared gamma and sigma squared epsilon are indeed in the neighborhood of 5. With the old design, we do not get close. With the old design, we get pretty poor estimates for sigma squared epsilon and sigma squared gamma. And we can again see that the old design does badly when it comes to estimating the variance ratio eta. So that's some of the results that we got for this example that shows the usefulness of this new criterion that takes into account variance component estimation when constructing designs. And then here's another table with computational results that we got. In this table, we show how often we got estimation problems when estimating the variance components from simulated data. And what we can see is that every time in each scenario, the numbers for the old design are bigger than the numbers for the new design. So with the old design, we got estimation problems more often than with the new design. And what do I mean by estimation problems? Well, by estimation problems, I mean, for example, zero estimates for sigma squared epsilon. You can see here, if eta is equal to 10 when generating the data, we get zero estimates for sigma squared epsilon in 753 cases out of 10,000 simulated data sets, compared to 531 for the new design. Large estimates we also consider problematic, and by large we mean estimates for sigma squared epsilon in the neighborhood of 100 or 1000. We can see that this also happens more often with the old design than with the new design. And similarly, when we count the zero estimates for sigma squared gamma and large estimates for sigma squared gamma, we can see that we encounter them much more often with the old design than with the new design. And we've also kept track of convergence problems when estimating the variance components. And we can see that also in terms of convergence problems, the old design does worse than the new design. That brings me to the final slide. So I've showed you a new design criterion with a dual objective, and the dual objective is to estimate both the fixed effects and the variance components as precisely as possible. Our new design criterion has a Bayesian flavor in the sense that we use prior distributions for either eta, the variance ratio eta, or the intra-class correlation coefficient rho, and we evaluate our Bayesian composite design criterion using quadrature approaches to save computer time. And I've also demonstrated to you that you run into problems less often with the designs generated with the new criterion than with the classical optimal block designs and split plot designs. What is also clear from our simulation results is that the new design criterion is not a panacea. It doesn't solve all the problems. If you keep on experimenting with very few runs, few whole plots, few blocks, you will still run into problems occasionally. You cannot solve, the new design criterion cannot solve everything. So that's a plea for larger experiments with more whole plots. Thank you.
Yeah, we can still take a few questions for Peter.
And just a comment that may not, well, I'm not sure if it's relevant or not, but if we were modelling means and variances using generalized linear models, we'd usually have a log link and a gamma distribution rather than a log and a normal. This probably doesn't make a lot of difference to what you're doing with your Bayesian criterion, but I wondered if you thought about having a gamma rather than a normal. Comment number one. Comment number two, modelling mean and variance with generalized linear models, we can't take account of negative variance components because of the log transformation, and nor indeed can you. But I think in practice that might be something that you ought to consider, not for the blocked designs, but certainly for the whole plots where you're doing the more complicated design because of experimental constraints rather than because of the need to decrease the within block variability.
Yeah, so
I wonder if you've got any ideas about prime probabilities for that.
yeah, we did not look into generalized linear models, so we didn't try that yet. But I guess we can extend the composite design criterion to these situations as well. As to your second comment, I guess we can adapt our prior distributions or use slightly different prior distributions to handle negative variance components in a way. But I would say in industrial contexts, I would find it very hard to come up with good explanations of why you can have negative variance components and negative variance ratios. So that
Competition effects, essentially. But yes, if you're doing sequential runs, then it's not. Field experiments,
Yeah.
it happens a lot.
Yeah, I can imagine that, but in the contexts that I work in, such competition effects seem unlikely and perhaps unbelievable. So that's why we focus on positive variance component estimates.
The original criterion focused on estimating the main effects, the fixed
Not
effects.
fixed effects.
Do you actually get, if you look at the ultimate estimates that you get, the sort of simulations that you have at the end where you're estimating the variance components, if you look at the estimates of the fixed effects, you also get actually better estimates of the fixed effects using the new criterion, with the intuition being your actual estimates have the estimated V in and not the real V. And you're obviously getting much better estimated V with the new criterion. And I'm wondering if this leads to better estimates of the fixed effects, even though that wasn't the goal.
Yeah, we looked at that also, and I deleted these results from my presentations for the sake of time. But the differences in the fixed effects estimation are not very big. And the reason is that the fixed effects estimates you get are not very sensitive to the exact eta value that you use.
Other questions?
I'd say the variance component estimation is very important for the inference, not so much for the fixed effects estimation.
Would be a clear extension to generalize the beta distribution, to extend the beta distribution to -1 to 1 to get robustness against the competition?
I think it will be easily doable if you use the pseudo-Monte Carlo sampling approach. I would not know whether there is a quadrature approach that can handle with the generalized beta distribution. Possibly there is, but I don't know by heart.
All right, so we have one final question.
How sensitive are the estimates to the number of points you choose in the quadrature? 4 just seems very small to me, and when I've used quadrature methods.
So the integral approximation is sensitive to the number of abscisses that you use if you use too few. But we did tests with 2, 4, 6, 8 abscisses, and 4 was the smallest number where we got good approximations. I should say for Gauss-Stieltjes-Wiegert. For different quadrature approaches, different numbers are used.
Okay, let's thank Peter again.